Welcome to this explainer. Okay, let's dive right into this. Today we're doing a total upgrade to our logical toolset. I mean, if you've ever felt that basic true or false statements just kind of fall short when it comes to capturing the sheer complexity of the real world, or the digital world, you are absolutely right. We are moving way beyond simple propositions today. We're stepping into the realm of predicate calculus, which literally gives us the power to reason about entire groups of objects all at the exact same time.
To see exactly why we need this upgrade, let's start with what seems like a totally simple question. How does a computer know that every single computer on its network is safe? Obviously, this is absolutely crucial for cybersecurity. But honestly, it immediately exposes a massive flaw in our basic, traditional, true or false propositional logic. It creates this sort of intellectual itch that our old tools just cannot scratch.
Just look at the difference here. Basic logic, it's great at dealing with isolated, super specific statements. Something like, Math 3 is functioning properly. That's a simple proposition, right? It's either true or false. Boom, done. But if we actually want to secure a whole network, that is not going to cut it. We need to be able to evaluate broad, sweeping, categorical statements like every computer connected to the university network is functioning properly. And the reality is, standard propositional logic simply doesn't have the vocabulary to handle the word every.
So here's our roadmap for the explainer today. First, we'll look at the limits of simple logic. Then, introducing predicates and variables. After that, the universal quantifier, followed by the existential quantifier. Then we're flipping logic with De Morgan's laws, and finally, translating English into logic.
All right, starting with part 1, the limits of simple logic.
Let's look at these two statements. Statement 1 is highly specific. CS2 is under attack by an intruder. Meanwhile, statement 2 is categorical. There is a computer on the university network that is under attack by an intruder. Now, intuitively, as humans, we know that if statement 1 is true, statement 2 absolutely must be true. But here is the crazy part. There are literally no rules in simple propositional logic that allow us to deduce the second statement from the first. None. The system treats them as totally unrelated propositions. We desperately need a system that actually recognizes the internal structure of these sentences.
Which brings us to part 2, introducing predicates and variables.
Okay, so a predicate is simply a property that the subject of a statement can have. We usually denote it with a capital letter like P, followed by a variable in parentheses like X. So we read that as P of X. Now this next part is absolutely crucial. A statement like X is greater than 3 or computer X is under attack is actually neither true nor false on its own. It's just kind of hanging there. It only becomes a proposition with a concrete truth value once you assign a specific actual value to that variable X.
Let's anchor this abstract math with a real-world network security example. Let's say A of X equals computer X is under attack. If we happen to know that currently only the computers named CS2 and MATH1 are attacked, well, then A of MATH1 is absolutely true. But A of CS1? That's false. And this brilliantly illustrates how predicates act almost like a fill-in-the-blank template. They only become concrete propositions with distinct truth values the exact moment we plug in a specific subject.
Moving right along to part 3, the universal quantifier.
Okay, so this is the tool that gives us the absolute superpower to talk about entire groups at once, without having to check items one by one by one. The universal quantifier is denoted by this cool upside-down A symbol. What it does is assert that a predicate, P of X, is true for all values of X in a specified domain. Now, the huge takeaway here is the domain of discourse. That's just a fancy way of saying the specific universe of objects we're currently talking about, and it must always be clearly specified. If you say, for all X, we kind of need to know what X actually represents, right? Is it all integers, all real numbers, every single computer on a campus? Without defining the domain, the statement literally has no meaning.
Now, I know the mathematical notation with that upside-down A might look dense, maybe a little intimidating at first glance, but it's really just shorthand. When you see this symbol next to an X, followed by P of X, just read it in plain English. It simply says, for all X, P of X is true, or for every X, P of X is true. It's an insanely efficient way to make a massive, sweeping claim about an entire system. But word of warning, if even a single item in the domain makes P of X false, which we call a counterexample, well then the entire universal statement is completely false. One bad apple ruins the whole bunch.
Let's flip to part 4, the existential quantifier. So the universal quantifier's partner in crime is the existential quantifier, denoted by this backwards E. This one asserts that there exists at least one element X in the domain such that P of X is true. Whenever you see this symbol, you just read it as there is an x such that p of x, or even for some x, p of x. Just like before, you absolutely must define your domain. But here is the big difference. While the universal quantifier is totally destroyed by a single counterexample, the existential quantifier is proven true the very second you find just one single match. If you have any background in programming, this is going to click instantly. Think of evaluating these quantifiers exactly like running a loop. For a universal quantifier, your mental algorithm loops through all the items. It only stops and returns false if it hits a counterexample. If it manages to finish the entire loop without failing, boom, it's true. On the flip side, for an existential quantifier, your algorithm searches through the items, but it stops and returns true the very moment it finds a match. If it finishes the whole search without a single hit, then and only then is it false.
Okay, let's take a super quick historical detour to rest our mathematical brains for a second. It's easy to forget that these deeply abstract foundational systems were built by actual, fascinating human beings. This guy here is Charles Sanders Peirce, an incredible 19th century polymath, and an absolute pioneer in logic. We're talking scientist, philosopher, inventor, the whole shebang. He realized that mathematical study could deeply expand the mind's powers of imagination. He really helped lay the groundwork for the exact logic systems we are upgrading to today, systems that honestly are utterly fundamental to modern computer science and artificial intelligence.
Back to the math with Part 5, Flipping Logic with De Morgan's Laws.
Let me guide you through this grid right here, straight from our source material. It outlines the precise rules for negating quantifiers, and honestly, the symmetry is pretty beautiful. When you negate an existential statement, meaning you're saying, it is not true that there exists an x, that is perfectly logically equivalent to saying, for every x, this property is false. And it works the other way too. If you negate a universal statement, saying, it is not true that for all x, this property holds, that is exactly the same as saying, there exists an x for which this property is false. Long story short, negating a quantifier simply flips it to the other type and then negates the predicate inside.
Let's look at a real-world example to really make this stick. Imagine the statement, not all Americans eat cheeseburgers. Now, what's so cool about this is that this negative universal statement is structurally and logically identical to the existential statement. There is an American who does not eat cheeseburgers. Both statements do the exact same logical heavy lifting. The negation of that universal claim translates perfectly into an existential claim about just finding one single counterexample. Finally, we've arrived at Part 6, Translating English into Logic.
Let's see how this all comes together systematically. Take the everyday sentence, every student in this class has studied calculus. Step 1, we rewrite it a bit more clearly. For every student in this class, that student has studied calculus. Step 2, we add in our variable. For every student x in this class, x has studied calculus. Step 3, define your predicate, let's call it c of x, as x has studied calculus. And finally, assuming our domain is specifically the students in this class, we get this beautiful, hyper-concise translation. The universal quantifier, meaning for all x, followed by c of x. By applying these new tools, a messy English sentence becomes completely simple and perfectly mathematical.
Which leaves us with this final thought to chew on. Logic isn't just about computers or dry math formulas, it's really about structuring how we understand the entire world around us. So, the very next time you hear a blanket rule in your workplace or some sweeping news headline on television, ask yourself, how would I translate that into predicate logic? Are they making a universal claim or just an existential one? What exactly is their domain of discourse? Equipping yourself with this logical toolkit doesn't just help you program better, it literally helps you think clearer. Thanks for joining this explainer, and keep upgrading your mind.